Alright, is this actually gonna fucking work this time? I have no idea. Holy shit, it is. Okay, there we go. Okay. God, I need a shock mount. Okay, let's get to my live dashboard. Shit. All right. Let's learn some motherfucking computer science, boys. I know a little bit of C#. I've made fuck, what's the game with the little ship at the bottom and you shoot up at the aliens? Fucking Galaga? Yeah, I made a Galaga clone in Unity. That's about all the programming I know. So this is an hour-long lecture. I am not sure if I need to watch all of this, to be honest. Can you believe there's no 1.25 speed in Windows fucking media player? Isn't that ridiculous, guys? You have 1 or 1.5. Why is there no compromise down the middle? Okay, can you guys hear my desktop audio? No. Let me fix that.
It's entirely based about programming. It's perhaps a bit antisocial. It's perhaps the computer lab heads down, sort of coding away on something that you don't necessarily understand. And yet, I too had that perception freshman year. And this course, and dare say the field more generally, really did have this reputation to beware. I certainly assumed that most everyone around me certainly knew more than I did. And this wasn't just true of CS for me. This was true of most any field at Harvard in the course catalog that I had no familiarity with. And so I instead gravitated toward the more comfortable. And so I instead gravitated toward the more comfortable. And so I instead gravitated toward the more comfortable. And so I instead gravitated toward the more I knew it, and it was within my comfort zone. And it wasn't until sophomore year that I got up the nerve to take this class, CS50. And I only did because the professor at the time let me take it pass-fail, now called sat-unsat. And that allowed me to get over this sort of mental hurdle that I had imposed upon myself, sort of fear of failure or simply not doing as well as I might have been accustomed to. And so I bewared a class like this until then. And I always kind of regretted not exploring earlier on. And that doesn't have to be this class, doesn't have to be CS, but can be really any field more generally. But those really were my takeaways around the time I looked like this. And I've taken comfort since in taking over this class and have found it inspiring that these days 68% of the students in this room and in this room last year had never taken a CS course before. So if you do have that mental model of everyone to your left and your right surely must know more than you, odds are it is not in fact the case. In fact, within CS50 we have these different tracks, different types of sections for students less comfortable, students more comfortable, and students somewhere in between. And there's no formal definition to these labels. You just sort of know it if you are. And if you kind of have one foot mentally out the door today because you're not really sure this is for you, you're probably among those less comfortable. But as such, you're in the majority, 56% of last year's students. If, by contrast, you have been programming since you were 8 years old, 10 years old, whatever, but you're largely self-taught and therefore maybe have lots of gaps in your knowledge or don't really understand all the formalities, you just kind of figured things out, you might be among those more comfortable. And if not, maybe you're somewhere in between. And so in CS50 sections, do we have similar students together, similar comfort levels, similar backgrounds, so that everyone can kind of feel comfortable speaking up, not knowing things, and beyond? Because ultimately, the course is graded and assessed ultimately very much manually, very delicately with respect to students' prior background or lack thereof. Indeed, what's most important at the end of the semester is not so much where you end up relative to your classmates, but where you end up in week 11, our very last week, relative to yourself today in week 0. And in fact, thanks to CS50's own Haley James and a whole bunch of CS50's team members this summer, they spent a while traveling around the country bringing folks back to campus, alumni of some of your predecessors and folks who sort of found their way accidentally even to computer science, finding challenges along the way. Check out this domain that the team put together, project5050.org. Now, the course itself ultimately is not about programming per se. That's indeed a tool that we'll use. It's really about this. And that's really what CS is, the fields more generally. Whether you're studying hardware or graphics or theory or any number of fields, and artificial intelligence these days, machine learning and beyond, it's really just about solving problems. And what's really cool about CS, I found early on, is that it doesn't necessarily, it's not an end unto itself. It's this field that empowers you to go do more interesting, more powerful things in the humanities, social sciences, physical sciences, the arts, anything, because you have this new mental model for how you can solve problems better, more efficiently, how you can solve them correctly, and how you can sort of analyze large data sets or solve problems that might have otherwise been beyond your grasp. So what does this mean? What is problem solving? Well, we could perhaps distill it as simply as this: a big black box, some secret sauce, into which go inputs, like the problem we want to solve, and out of which comes outputs, the solutions that we want. So a very generic way of describing it, but what's pictured here in the black box is the so-called algorithms. And we'll come back to that in just a bit, the actual ingredients for solving problems. But how do we represent inputs and outputs? Odds are, even if you're not a computer person and don't really think like one, you probably know that computers only understand a very limited vocabulary. Like, what is the alphabet, so to speak, that they speak? ASCII maybe, but more binary. Bi meaning 2 for zeros and ones. So whereas we humans typically use decimal, dec meaning 10, 0 through 9 is in our alphabet of letters, computers, of course, as you may have heard, only use zeros and ones. Now, why is this powerful? Well, it turns out as soon as you have at least 2 digits in your alphabet, you can start to represent things much more powerfully and much more efficiently. For instance, if I wanted to count the people in this room, how many of you could I count on just one hand? All right, hopefully 5, so I could count 5 of you. 1, 2, powerfully and much more efficiently. For instance, if I wanted to count the people in this room, how many of you could I count on just one hand?
5.
Hopefully 5, so I could count 5 of you. 1.
Well, okay. Theoretically 6, because you could do, like, you could put your arm down like this, and you can put like 1, 2, 3, 4, 5, and then you go put your arm up for 6, right? So actually, you could count 6 people on one arm.
1, 2, 3,
right.
4.
Dude, and then like you could do like a whole system. You could have like the middle could be like 0, so it's like, 1, 2, 3, 4, 5, and then up could be like 6. But then like down could be like 7, right? So then you can count 7 on one arm. I mean, we're thinking about efficiency here, right?
5. But you know what? If I were a little more clever, I bet I could use the same hand and count as many as 32, or maybe 31 of you.
Dude, holy shit. I thought 32 people on one. Dude, I thought 7 was a lot. Dude, I thought I was breaking ground here. Fuck.
How is that? Well, right now I'm kind of using the unary system. The uno meaning 1, so it's just 1 digit in your alphabet, the finger or no finger. It's not quite the same as 0 or 1, so 1 person, 2, 3, 4, 5. But what if I instead permuted my fingers in some way so that the pattern of fingers that are up actually matters, not just the quantity? So
dude, I was already ahead of him there, bro. I was already ahead.
Maybe this is still 0. This now is 1. And instead of 2 being this, maybe 2 could be this. So if my second finger is up, I'm going to call that 2. And if my first 2 fingers are up, I might call that 3. Somewhat offensively, if just this finger is up, I might call this 4. And then 5, and then this gets kind of painful, 6, 7, and what I'm actually doing is counting in binary. Now, that might have looked completely cryptic, but it turns out as soon as you have 2 digits, that's enough to represent anything you want and to do so pretty darn efficiently. But why? So odds are, if you're like me, you probably grew up learning, of course, the decimal system, 0 through 9. And you might have written on the board some point like this number, 123. But why do you think of that as 123? It's really just a pretty pattern of symbols, glyphs, so to speak, on the screen that we ascribe some kind of mathematical meaning to, 123. But really, it's just like someone drew in ink on the screen some symbols. Well, if you're like me back in grade school, you probably learned that the rightmost number here is in the so-called what place? The ones place, right? And so if we wanted to label these things, we might put ones place there, and then, of course, the tens place, the hundreds place, maybe the thousands, 10,000, and so forth. So we had these sort of mental models for the columns. And notice they happen to be powers of 10. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 2 is 100, and so forth. So that's the pattern, even if your grade school teacher didn't talk about exponentiation at the time. So why is this number 123? Well, it's because we have a 1 in the hundreds column, so 100 times 1. We have a 2 in the tens column. We have a 3 in the ones column. And of course, if we start to do the arithmetic now, that's 100 plus 20 plus 3, or obviously 123. And all of us take that certainly for granted these days. You see a number, you know what it is mathematically. But computers fundamentally work in the same way. So any of you up until now have never thought of yourself as a computer person or had no idea really what it means for computers to speak just zeros and ones, all you have to do is update the places. Instead of powers of 10 for dec, meaning decimal, we're going to have powers of 2 for binary. So now we're going to have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Same idea, it's just a different base. We changed 10 to 2. Base. And so now we have places like this, 1, 2, 4, and if we kept going, 8, 16, 32, 64, and so forth. So as such, what number is this on the screen in binary if you convert it in your head to decimal? It's just the number 1, right? Because you've got a 1 in the ones place, and then a 0 in every other place, so it's just 1 times 1 equals 1. Now, if I were using unary, or my hands, the sort of traditional way, 2 would be this, where you put up 2 fingers, but not if you're trying to use patterns as well as quantities. And so in binary, how do I represent the number 2? 0, 1, 0. It's the equivalent of putting up just my index finger here. And if I want to count to 3, now I need to add a 1 to the mix, so I add the ones place. And now, if you sort of start to visualize this, it's like one of those really old school clocks where the numbers flip around and roll over. Now those ones are going to kind of flip and become zeros, and the 0 is going to become a 1. And so now we have 5, and then 6, and then 7, and then, dang it, how does a computer count to 8? Yeah, you just need to add another place, right? Just like we humans don't have an infinite number of numbers when we write something down. We sort of stop when it's not necessary. All we need is another bit. We just need to add another 0 or 1 to the left, specifically a 1, and all these ones can become zeros. And we can do this toward infinity. But where are these bits coming from? This is all very abstract and just pictures on a screen. Well, it turns out that we have fun physical ingredients to all of our computers. Maybe it's your laptop or desktop or your cell phone. At the end of the day, they're either driven these days by batteries or like a cord into the wall where electricity comes from. And even if you have little familiarity with electricity, you probably know that it's like little electrons flowing. So there's some kind of physical resource that can flow or not flow. You can turn it on or off. Well, much like these desk lamps here, I have 3 physical lights. They're, of course, connected into the electricity, so I have some physical input. And now that I do, I can kind of implement my own computer using these simple desk lamps. If I want to represent some value, some input or output, OK, here's the 0. This is 0 in binary. I just need to leave 3 light bulbs off. If I want to represent a 1, I need to turn this on, and that's now the ones place. If I want to represent 2, I just need to turn this light on. If I want to represent 3, this one comes on. If I want to represent 4, that goes on. 5, 6, 7. And then, of course, we need like 8 if we want to represent and turn these off 4 total bits together. And so that's all that's going on inside of your phones and your computers. Phones and computers and devices these days have what are called transistors, which are tiny little switches that are on or off. And that's all we need if we have some source like electricity to just store information. We just need lots and lots of switches, lots of light bulbs, certainly much smaller, in order to represent information. But computers, of course, can do much more. then represent numbers. What about letters and
Really?
emails and things like that? Well, for that, we actually need to kind of decide as humans how we're going to interpret things like these light bulbs. In one context, like a calculator, they might represent numbers, decimal numbers, whatever. But in an email program, Microsoft Word, Google Docs, you probably want those light bulbs or those transistors in the computer storing not just numbers, else you could just do math. You want them storing letters and sentences and paragraphs and so forth. And so we need to have some kind of mapping. And we'll do that as follows. ASCII, which is just an acronym describing a mapping from numbers to letters. Humans, years ago, just decided, you know what? In the context where we need letters, let's just store a pattern of bits that's equal to the number 65 if we want the letter A. Pattern of bits equal to the number, decimal number 66, if we want to store the number B. Fast forward to H and I, if you want to store H or I, 72, 73, and just store that many bits. And now, I don't care anymore in this story how you represent 65 or 73. I just need to know that you can somehow, with light bulbs on stage, with transistors in my phone, or whatever the device may be. We can begin to abstract away these low-level details. In fact, we're not going to spend much time after today talking about binary in CS50, because here we have sort of electricity conceptually. On top of that, we can build the notion of binary, zeros and ones. And once we come up with this convention, now we can start to talk about letters of an alphabet. But that's not the only thing we can talk about. We can also talk about graphics and videos and all of the things we take for granted these days. For instance, and just to recap, what message have I encoded here on the screen, if you recall? Hi. Yeah, it's hi, because 72 and 73, I claimed a moment ago, are just the numbers we humans came up with years ago to represent HI. I don't really know what 33 is. You'd have to look it up or be told it. Turns out it's an exclamation point, because indeed humans decided to express in numeric codes as well all the keys on a keyboard. Unfortunately, they weren't very far-sighted early on. They only used 7 bits total, and later kind of 8 bits. But even that, even though that gives us over 200 possible values, 256, there's a lot of languages that aren't written in like the English alphabet, Asian languages and the like, that have many, many, many more symbols than you can express with just 7 or 8 bits alone. And so now ASCII has been succeeded by something called Unicode. And long story short, humans have begun to solve problems that were initially created by not anticipating needing or wanting even larger values than these. But in another context, like Photoshop or any graphics program, you might see the same pattern of bits, 72, 73, 33. But in those programs, they know to interpret these numbers as some amount of color. If you've ever heard of RGB, red, green, blue, this is just an acronym that describes how you can mix together 3 different colors, sort of in the spirit of paint, or more technically light, combine these 3 different colors, and get any color of the rainbow. So each of these numbers, I'll claim, can be from 0 to 255. And 72 out of 255, that's like a medium amount of red. That's like a medium amount of green, and just a little bit of blue. And if you combine those 3 colors by mixing them together into just one dot, or pixel, as it's called in a computer, you get this sort of murky shade of yellow. But in the context of Photoshop or some graphics program, that is what those same 3 patterns of bits would be interpreted as. And it happens to be the case that talking in terms of single bits, it's not all that useful. With 1 bit, you can count as high as 1. So humans long ago also standardized on a nomenclature. A byte, B-Y-T-E, is just 8 bits. And if you've ever heard of kilobytes and megabytes and gigabytes and terabytes and the like, those are just multiples thereof, typically orders of magnitude of 1,000 or 1,024 or more. So with just 3 bytes, 24 bits, can we represent letters, numbers, or the like? And ultimately, these are just examples of abstraction. And this is going to be a theme that permeates not just this class, but computer science more generally, taking very simple ideas that really don't seem all that interesting at first glance, but as soon as you use them as ingredients to solve a problem, you can then sort of reuse that tool to build something more interesting, reuse that tool to build something more interesting still, until you get to work with application development and solving real problems that you care about, taking for granted that people that came before you have solved a lot of these lower level implementation details, so to speak. So what is inside this black box? It is what we shall call algorithms. And an algorithm, if familiar, is what? It's kind of a fancy looking word, but it's a simple thing. What is an algorithm, if anyone knows?
Set of rules.
Yeah, just step-by-step instructions for solving a problem. That's it. That is
Got
an
it
algorithm.
right, dude.
Step-by-step instructions for solving some problem. So what might be a problem that we want to solve? Well, I'm reminded of, and I'm reminded of 5th grade. my homeroom teacher was trying to teach us as effectively as she could how to follow directions correctly. And at the time, it was a complete disaster. But I always remembered from that example the demonstration that she did, because it lent itself, although she didn't use this word at the time, to this notion of computational thinking, or thinking like a computer, if you will, whereby you want to solve something correctly. But to do so, you need to be fed very precise instructions. And this is easier said than done. And so in fact, to recreate this, thanks to the team here, we have a plate. We have a loaf of bread. We have a jar of creamy Skippy peanut butter. And we have a jar of Smucker's Concord Grape jam. And then for the invariable need, a whole lot of paper towel and this one knife. And so let me propose that for just a moment, I'll play the role of a computer, or maybe in this form, like a robot who's implementing some algorithm, where you guys are the programmer, the person who's supposed to feed me instructions so that I can solve a problem. And the problem here will be to implement, perhaps no surprise, a peanut butter and jelly sandwich. Easy to sort of do intuitively if you grew up eating these things. But if you've never really thought about how to teach someone else to do it, and that someone else is not as sort of forgiving as another human, where we humans have conventions of just reading between the lines, computers can't do that. They will only do what you tell them to do. And as such, they are less powerful in some sense than we humans. So what's the first step for making, with these ingredients, these inputs, if you will, a peanut butter and jelly sandwich? Open the bag of bread, I heard. Correct, but not really what you had in mind, perhaps. But that's OK. The bag is open. So what might a more precise step 2 be? Say again? Remove 2 slices. OK. Put those 2 slices on the plate. Drop the knife? OK. Unscrew the jam. OK. Grab the knife. Put the knife in the, what? Oh, thank you. Right. Grab the knife from the other end.
Dude,
someone from farther back, perhaps?
Bro just grabs the handle full of jelly like a champ.
Stick the knife in the jam.
That's crazy.
What's that? Take it out. OK. Again. Put the knife in the jam. Ow. Scoop it. OK, we're halfway there. Now what? Spread the jam with the knife across the bread. Oh, evenly. Let's be careful here. OK. Right. OK. OK. Next. OK, so I think we did this first. We did this, then we did that, then, OK, I'll take some liberties. OK, and now we put it in again. Scoop a little bit out, I heard this time. Onto the other slice of bread, thank you.
How to define a little bit.
Spread it evenly.
How many grams of peanut butter?
Next time, have me use my right hand, please. OK. OK. And? Thank you. Put the jam side on the peanut butter, and delicious. OK. OK. Thank you very much. So a silly example, to be fair. But just realize how much opportunity there was, even in something as simple as that, for ambiguity or scenarios you didn't anticipate. And indeed, among the things we're going to do today as we begin to formalize these ideas with code, with programming code, are how you think about breaking down problems into their constituent parts, considering what should I do if this happens? What should I do if this happens? What should I do if this happens? Because unless you anticipate the kind of silliness that I was deliberately acting out there, who knows what the computer might end up doing. After all, odds are everyone in this room, like me, has seen like a spinning beach ball or an hourglass on your computer, or your Mac or PC freezes or crashes, and almost always that's just the result of some human error. Someone at Google or Microsoft or Facebook or wherever made some mistake. He or she did not anticipate some situation, didn't anticipate you typing in a word that you didn't anticipate you running 20 programs at once, didn't anticipate some scenario, and so as such, the computer's behavior was effectively undefined, and so the incorrect solution was outputted. So how do we begin to think about this? Well, it would be ideal if we somehow formalize this by way of actual code. And we'll do that with sort of another old school problem, one that's a lot more digital these days, but it's still with us today. Whether you have an Android phone or iPhone or anything else, odds are you have like a little app for your contacts or your address book, and in there are a whole bunch of names, probably alphabetical by first name or last name, and a whole bunch of telephone numbers and maybe more information like emails and so forth today. But the physical incarnation of that icon on your phone is this old thing, a phone book. And if I wanted to look for an old friend like, say, Mike Smith, how might I go about finding him in this old school phone book? Well, just as in my digital form, I might just scroll through the list looking for him. So could I look at the first page, look down, not see him, turn the page, look down, not see him, turn the page, look down, not see him, and so forth. Is this algorithm correct? Yeah, it's correct. It's kind of dumb, right? Because it's going to take forever to get to Mike if there's like 1,000 pages here, but it is correct. And it's the equivalent, really, of sort of slowly, methodically scrolling through your list of contacts without the luxury of like searching or autocomplete or the like. Well, I could do a little better. Back in grade school, I generally learned to count by 2, so I could instead do 2, 4, 6, 8, 10, 12. I'm flying through the phone book now, clearly faster. But is that algorithm correct? No, why? Yeah, I might miss some, right? Like Mike, just by chance, might be sandwiched between, so does, no pun intended, between the 2 pages that I'm flying past, and I might miss him. But I can at least fix this mistake or bug, so to speak. A bug is a mistake in a program, just human error. If I hit like the T section, T comes after Smith, so I could maybe double back at least 1 page and solve that bug. So it costs me a little bit more time to double back, but if I do it right, it only costs me like 1 extra page turn. So better, and now correct. But obviously, no one in this room is going to look for Mike Smith by starting on the first page. Where are you going to roughly look? You know, in the middle, maybe a little toward the end, because you know where S's are. And so you open the book to the middle, you look down, and you see the M section. So I haven't gone far enough. But what's nice about this old school technology is that we can now tear this problem in half, throw half of it away, and be left with fundamentally the same problem, but a smaller version thereof. This now is maybe not 1,000, but 500 pages. But it is the same problem. And I can apply the same logic, go roughly to the middle, look down. I went a little too far this time, the T section. But I can again tear off almost a quarter of that problem, leaving me now with a total size of maybe 250 pages after dividing in half twice now. And now I can repeat and repeat and repeat. And so long as Mike is in the phone book, I should ultimately find him once and only once on the final page of the phone book, at which point I can call him. So the real question then is, how much better was this? It's a little wasteful. You can't sort of undo here in the analog world. But let's consider how we can think about how good that algorithm was, the one that we all probably took for granted and should have started with. Well, if here's a simple plot, and on the x or horizontal axis is the size of the problem, so number of pages in the phone book, or however you want to measure it. And then the y or vertical axis is time to solve, so maybe number of seconds, number of page turns, however you want to count up the steps. That's a relationship, size to time. And the first algorithm, I'm going to draw like this, a straight line in red. And I'm going to call it n, where n is just like the number of pages in the phone book. Computer scientists tend to use n as a variable, so to speak, just a symbol. And it's a straight line for the following reason. If the phone book gets a little longer next year by like 1 page, that means I might have to spend 1 more step looking for Mike. So the slope of this line is linear. There's a 1-to-1 relationship between number of pages Verizon or the phone book company puts in the book and the number of page turns I need to make. The second algorithm, though, is also a straight line, but it's lower, drawn here in yellow. And n over 2 means it's twice as fast, or equivalently takes half as much time, because for a given size problem, if you kind of follow my hand straight up, the yellow line should be below the red line, because I'm flying through the phone book 2 pages at a time, so it should take me half as much time. But if I use the first algorithm, I have to go all the way up to the red, which measures that number of seconds. But the third algorithm is a fundamentally different shape. And this is where the sort of beauty of computer science and algorithms specifically comes out. It doesn't become straight ultimately. It looks like it's gradually easing off, but it's going to do this forever. It's just becoming such a slow increase in time, you can't even really see it, especially if the screen were even wider. And we'll call this logarithmic, log n, more on that down the road. But the shape is fundamentally different. It's curved. And what's powerful about this, and you can think about it much more easily intuitively, if Verizon next year doubles the size of the phone book, because like maybe Cambridge and another town merge together into one book, no big deal. Because if Verizon doubles the size of the phone book next year, how many more page turns do I need to find Mike? Just one, right? Because I just split the problem in half one more time, no big deal, instead of flipping through an additional 1,000 or 500 pages. And so this intuition with which you entered Sanders today, odds are you can harness it already to solve problems more effectively, so long as you start to notice the patterns and the sort of useful inputs with which you can solve problems. But we need to begin to formalize the process. We need to be able to express ourselves a little less organically than we did with the peanut butter and jelly. So how might we more methodically express that algorithm, the phone book, all of which, for which we probably nonetheless have an intuitive understanding? Well, let me start counting at 0, just because programmers and computer scientists tend to start counting at 0, because that's like all the light bulbs are off, so you might as well start there. And then step 0 would be pick up phone book. It's sort of an action. Do this. Step 1 is open to the middle of the phone book. That's pretty much what I did a moment ago. Step 2 is look at the names, another action or verb. Step 3, if Smith is among names. So this is a different construct. And that keyword here is going to be if. It's a question you're asking yourself. It's kind of a proverbial fork in the road. If Mike is among the names on the page you're looking, then call Mike. And I've deliberately indented it because in many computer languages, indentation means logically that you.
All right, boys. I'm going to go eat. And then I'll be back on stream to learn more computer science.